Hello and welcome to another in OpenEye Cadence Molecular Sciences series of scientific webinars. Today's presenter, Chris Neale. For those of you who don't know Chris, he was a graduate student at the University of Toronto, postdoc at Rensselaer Polytechnic Institute, RPI, and a staff scientist at Los Alamos National Lab in the Theoretical Biology Group. Currently, he leads the Affinity prediction group here at OpenEye and is also a member of the Biophysical Journal's editorial board. So it's a great pleasure to have Chris. Welcome today.
Hi, Paul.
So tell us, what's the title of your talk? What are you going to be talking about today?
I'm excited to talk to you today about optimizing lead compounds with efficient binding free energy calculation.
I was hoping you were going to say something like that. Great. So I shan't intrude any longer. Please, Chris, take it away whenever you're ready.
OpenEye offers a variety of tools for molecular ideation and posing those ligands. What I'm going to talk about today is the top right of this plot, where we offer tools that can help you to rank order those molecules and make actionable decisions about which molecules you want to actually make and which ones you don't want to make. More specifically, I'm going to be talking about how OpenEye affinity flows can help you with ranking during lead optimization. This talk is going to be divided into 3 parts. I'm going to start by going over the accuracy and utility of our affinity flows. Then I'm going to talk about how we can help you to put more molecules through those flows on a weekly basis. And I'm going to conclude with some of the new features. So we like to think of these tools as existing within a conceptual funnel in which the methods get more accurate as they get more computationally demanding toward the bottom of the funnel. We can place some specific measures on this schematic. So for example, in screening and posing, we have our docking score, ChemGauss-4, which is very rapid. Can also take those docked poses and put them into a single point end state free energy calculation using molecular mechanics Poisson-Boltzmann solvent accessible surface area. Moving down the funnel from there, we can run some short molecular dynamic simulations, collect the ensembles of those trajectories in which we have some thermalization and relaxation in the context of explicit water, and then run MMPBSA on those conformations and get an ensemble average MMPBSA score. Finally, at the bottom of the funnel, we've got our heaviest and most accurate approach. It's a relative binding for energy approach called non-equilibrium switching, or NES. So I'm going to start by looking at the utility of these various methods across 16 different protein targets, each of which has 15 to 45 associated ligands. The collated references for those data sets are in the top right here. And I'm going to be comparing them with Kendall's tau. This is a measure of rank association between the prediction or the scoring method and the experimentally determined affinity for each ligand. For Kendall's tau, larger is better, and 1 represents an absolutely perfect rank association. So your top ranked ligand would be the top experimental ligand, and so on. So in this plot on the left, in each of these strip charts, each point represents the Kendall's tau for 1 protein target and all of its ligands, as that method can be used to compare to the experimental affinities. On the left, we've got the ChemGauss-4 score. That's our docking score, which has a broad range, but quite surprisingly actually provides utility for some of these data sets. As we move to the middle strip chart, that's the endpoint MMPBSA approximation, which is statistically significantly better across these 16 data sets. But in fact, ChemGauss-4 can be better than MMPBSA for a single target. And then on the right, I've got the much heavier ensemble averaged MMPBSA score following some molecular dynamic simulation. So as we move from left to right on this plot, we're actually moving down the funnel to methods that tend to become more accurate as they tend to become more computationally demanding. Another way of looking at this data is to just ask which method is the best for each of those 16 targets. So this is just a histogram showing that for 5 of those targets, our ChemGauss-4 docking score was actually the best of these 3. That's quite surprising because it's not what it was designed for, and it's very fast. But then for 11 of the 16 targets, either MMPBSA or the ensemble averaged MMPBSA had a larger Kendall's tau. Here the vertical bars are the 95% confidence interval. Another way we can try and understand this data is just by looking at the scatter plot between taus from two different methods. So again, each point is the Kendall's tau for one target data set. Horizontally, it's in this case the Kendall's tau from our ChemGauss4 docking score, and vertically it's the Kendall's tau from the MD ensemble average MMPBSA score. And what you can see here is that the more computationally demanding approach is either similarly accurate or more accurate than ChemGauss4 when we look collectively, even though in some cases, ChemGauss4 is outperforming this ensemble average MMPBSA. I told you that our most accurate and most computationally demanding method is called non-equilibrium switching. On the right, this is a movie of a non-equilibrium switch where we're directly morphing one ligand into another ligand. And in this case, we've got a hydrogen that's disappearing and an alkyl cyclohexyl that's appearing in its place. That's what's in green. Of course, this change in chemical identity is happening in explicit water and in the context of the protein binding pocket. We're going to run this switch very quickly, and we're going to do that 80 times. We're going to do it 80 times from ligand A to ligand B, and then 80 times from ligand B to ligand A, and we're going to do all of that in the protein binding pocket and in solution. And then by combining all of that, that gives us an estimate of the relative affinity between these two ligands, which one is going to bind more strongly. By then running those relative binding for energy calculations across many pairs of ligands, we can bring all that data together and get a per ligand estimate of the binding affinity for each ligand to the protein target. So this is similar to the plot I showed you before, but now I've added on the rightmost strip chart the non-equilibrium switching. Remember, we're going down the funnel as we go from left to right on here, and this is a statistically significant improvement over all of the other methods that I'm showing here when looked at collectively. Again, we can look at which method is the best, and so for 10 of these 16 targets, NES has the largest Kendall's tau with experiment. But even here, ChemGauss4, the simple, very fast docking method, is giving us the best Kendall's tau for 2 of those targets. Finally, we can again look at this scatter plot. Now the horizontal axis is the MD ensemble averaged MMPBSA Kendall's tau with experiment, and vertically is the NES Kendall's tau with experiment. And once again, the heavier method is either similarly accurate or more accurate than the lighter weight method, but again, it's target dependent and ligand series dependent. So that was a collection of statistical data across 16 different targets. I just want to show you what that looks like from one target. This is the non-receptor tyrosine kinase 2 protein target. And now each point is a ligand. So horizontally, it's the experimental affinity. Vertically, in this case, it's the single endpoint MMPBSA score. And I've circled the 3 ligands which would come out at the top of the ranking if one were to use MMPBSA to decide which ligands to make. And what you can see is the Kendall's tau here is basically 0. Those 3 ligands that we might make are distributed across a wide range of experimental affinities. In this case, this isn't a very useful method for identifying molecules to make and test. We move to the ensemble average MMPBSA. You can see that we're starting to get a slightly higher tau, still not a very useful relationship. We're starting to push those 3 selected ligands to the left, which is enriching in higher affinity. But when we move on to NES, you can see that we've now got a very robust correlation. In fact, the 3 ligands at the front of our rank ordered list from NES are within the top 5 best binding ligands from experiment. So in addition to comparing these methods between one another, we can compare them to methods that are available outside of OpenEye. So here I'm comparing our NES to Schrödinger's FEP+. And this is for those same 16 protein targets. I'm still comparing by Kendall's tau. Larger is better. And for each target, I've got a bar in blue for the NES Kendall's tau and a bar in yellow for the FEP+ Kendall's tau. I've arranged the targets from left to right on the bottom such that NES most outperforms FEP+ on the left, and FEP+ most outperforms NES on the right. And so what you can see is there are a variety of different performances for different targets. For SHP2 and EG5, FEP+ is dramatically outperforming, would be much more useful for those targets in your DMTA cycles. And on the left-hand side, thrombin, CDK2, CDK8 are providing more value from NES in terms of your weekly DMTA cycles. Here I'll note that we actually repeated all of these NES calculations, and the black bars are representing the variance, and where they're not showing up, it's because the the two estimates gave the same Kendall's tau. So similar performance overall, varied performance per target. On the right, what I've done is I'm trying to just compare these 16 targets collectively, and I'm showing the delta Kendall's tau. This is the NES Kendall's tau for one target minus the FEP plus Kendall's tau for that same target. Each point is a target data set, and points greater than 0 are ones for which NES is outperforming FEP plus, and below 0, NES is underperforming FEP plus. So collectively, there isn't a statistically significant difference in utility or accuracy with these two methods from a paired t-test, but on a per target or a per ligand series, you can find methods that outperform other methods in this space. So then bringing that all together, now I'm just showing raw Kendall's tau. Again, larger is better. Vaguely going down the funnel from left to right, where we've got the two heaviest methods, NES and FEP plus on the right. I showed you that they're not statistically significant in terms of Kendall's tau performance when you're looking at these 16 data sets collectively, but they are statistically significantly better than all of the methods that would exist kind of upwards in the funnel from them. On the far left, I'm adding something new. This is the negative heavy atom count per ligand correlated with the experimental affinity. And there's a large spread, but it's surprisingly large. And that's because these data sets are somewhat pathological. They're drawn from many months of DMTA, in which ligands do tend to become larger over time, and they do tend to become more potent over time. So they have this kind of built-in association between the size of the ligand and the affinity of the ligand. And so one might ask, are these heavier methods just kind of adding something on top of that, or are they doing something orthogonal? So one of the ways that we address that is by looking at in this case, the TIC2 protein target data set. And we're looking at both the relationship between experimental affinity and NES on the left, and the relationship between experimental affinity and the ligand size in the middle. So what you can see is that we are predicting this ligand in a very useful way on the left, this set of ligands for this target. And in the middle, there is no useful size correlation. That's why I picked this target to show. So this is an example to demonstrate that in the absence of a size relationship with affinity experimentally, we can still provide very useful rank correlation. Another thing we can do, though, is just directly assess the ligand efficiency. So on the plot on the right now, I've divided the experimental affinity by the number of heavy atoms, and I've divided the NES prediction by the number of heavy atoms. That's a per ligand basis. And even in the context of ligand efficiency here, we're seeing a robust correlation. We can then look at that across, again, all 16 target data sets. The Kendall's tau on the left is what I showed you before. This is just the raw NES Kendall's tau. And on the right, I'm now correcting to show ligand efficiency, where you can see that there are 3 target data sets with very low Kendall's tau, but the other 13 of the 16 target data sets have Kendall's tau ranging from 0.4, which is beginning to be useful, up to almost 0.8, which is a very strong and useful relationship in rank order. So I've been talking about these in terms of Kendall's tau, which is what I'm showing on the left. We rank order the ligands, and then we ask, how well does that rank order match the experimental rank? And that's absolutely the way to compare two methods on large data sets like this. But in your weekly DMTA cycle, it's not always clear that it matters that you can predict all of the ligands accurately. In fact, you're very likely going to rank order them, pick some of the predictions from the front end of that rank ordering, make those ligands, and as soon as you make that decision, I would argue that it no longer matters the internal order within the ligands that you're going to make. Likewise, it doesn't matter the internal order within the ligands that you've decided not to make. If you miss a ligand by a little bit or a lot, and that was a very potent ligand, you've still missed it. So I'm going to go over something called the overlap coefficient, which tries to quantitatively assess the utility of these methods at the front end of the prediction. So on the left is a schematic. The overlap coefficient is the proportion of the ligands that are actually the ligands with the highest affinity from the set of ligands that are predicted to have the highest affinity. And in order to do that here, we're just going to define N as the number of ligands we're going to make. So in the middle, I've got the protein target junk1. It's a scatter plot. Each point is a ligand. Horizontally is the experimental affinity, vertically is the NES prediction. And first you can see we have a good correlation. And then I've added 2 lines. So below the blue line are the ligands that come out at the front of the NES prediction. And to the left of the vertical brown line are the 4 ligands with the highest affinities experimentally. And then if you look in the lower left quadrant, we've captured 2 ligands. So of the 4 best ligands experimentally, we decided to make 4 based on this rank ordering. We captured 2 of the best. So that's kind of worked out for different values of n on the right-hand side. And we selected n as 4. We captured 2. It's a ratio of 0.5, and the random expectation there is 0.2. So you can calculate then the enrichment over a random expectation that your method is providing. So I'm going to then compare again NES in blue to FEP plus in yellow. This time I'm going to use the overlap coefficient. Because these target data sets have different numbers of ligands, I'm just going to say we're going to make the top 20% of ligands in each of those data sets. So that's a variable number of n between targets. And then I've arranged the targets from left to right in the exact same way I did before, by the relative performance of Kendall's tau. That means that the 4 targets on the right are the ones for which NES was most underperforming FEP plus in terms of Kendall's tau. But you can see here that we're performing equally well. And what that says is that NES was just as good at pushing the most potent ligands to the front of the rank-ordered NES list, even though it clearly wasn't as good at rank ordering some of the ligands that were had lower affinities within those data sets. But still, you see variance between the methods. For PTP1B, you've got a higher overlap coefficient for FEP plus than NES. For thrombin, you've got a higher overlap coefficient for NES than FEP plus. So we can come back to a plot like this where I compare all of the different methods. On the right, you've got NES and FEP plus. Now we're looking at the overlap coefficient of the top 20%. Again, pair t-test shows no statistically significant difference between those two, but they are better than the methods that exist higher up in the funnel. So I want to talk now about how you can increase the number of ligands that you can push through these computational approaches on a weekly or monthly basis. And the first way we do that is simply by our selection of method and the default settings that we provide. So on the right here is a comparison of the total amount of molecular simulation time required to run the CDK8 test set. The blue bar is the total time for our MD and NES switches, and the yellow bar is the total time with defaults for running Schrödinger's FEP plus. So you can see there's about a 5 to 6-fold difference there in the total amount of simulation time that's required. We also provide a method that's highly parallelizable. You can run all of these switches at the same time, and that can reduce your time to solution, giving you higher throughput. Of course, this also runs on Orion, which can grab 1,000 GPUs over the course of an hour, run all those switches, and then drop them, and you stop paying for the GPU usage. But we can also, within our method, look at some of the settings that we have to see whether there's trade-offs between accuracy and capacity, the number of ligands you can put through. And that's what I'm going to assess here. By default, we run 6 nanoseconds of MD per ligand in its end state, and then we run 80 NES switches. Those are those fast 50 picosecond switches. So the question here is, what would happen if we just ran shorter MD and fewer switches? So what I did was I took the data from all those 16 targets that I've been showing up until this point, and I have the data with 80 switches, and I can calculate that from that the mean absolute error for each of the ligands. I can then recalculate, what if we only ran the first half of the MD and the first half of the switches, or the first quarter? And I did that for a variety of switches per edge, all being less than 80. And that's what I'm showing on the left-hand side. This is a delta mean absolute error. So it's the mean absolute error for running a specified number of switches per edge minus the mean absolute error with 80 switches per edge. So that's why the point at 80 here is 0. And the error does increase as you run fewer switches after shorter MD. But this is a very long tail. If you're to look at the data point for 20 switches per edge, for example, that comes at an average cost of about 0.2 kcals per mole of increased error. So a plot like this allows one to look at this trade-off and say, if I ran 1/4 the switches, turns out that lets me put 3 times the number of ligands through my assay at the same computational expense. Can I accept an increase in average error of 0.2 kcals per mole in order to run 3 times as many ligands? Here I'm showing you a similar plot now for the Kendall's tau and the overlap coefficient. These show here increasing error is represented by a value that becomes less than 0. And these are even shallow or longer tails. And a large reason that is because these are large data sets taken from many months that span 4 or 5 kcals per mole in affinity among the ligands. It's likely that in a weekly DMTA setting, these Kendall's tau and overlap coefficients would see larger effects, slopes more similar to what we see on the left. So that was a retrospective analysis of data that was run with the default settings. Here I've taken the CDK8 protein target and I've run it repeatedly in 2 different ways. On the right, I've used all our default settings, and I'm showing that the correlation horizontal is the experimental affinity, vertical is the NES predicted affinity. And then on the left, I just ran MD as a quarter as long, and I ran a quarter as many switches. And it's true, the correlation is a little less, and the errors are a little larger, but I could put 3 times as many ligands through using the settings on the left for the same computational expense as the settings on the right. Another way that we help you to look at this trade-off between accuracy and capacity is by the types of binding for energy calculations that we run. So we provide you with an edge mapping flow that will connect the circles, which are the ligands, by edges, which is the actual RBFEs that we're going to run. And our default is OE low map. That's what's shown on the left. And it has characteristically 1.5 times the number of edges, the number of calculations, as there are ligands. And it has some nice properties. It has cycle closure that can help to identify errors and correct errors. The star map has the advantage of having only 1 edge per ligand. So that's 2/3 the number of calculations for OE low map. Now, it doesn't have cycle closure, but you can start to compound selections like star map with 20 switches per edge to really start increasing the capacity of these computational assays. We also offer the binary star map, and we're introducing now a multi-star map, which is conceptually like a star map, but it starts by clustering the ligands, which if you have very disparate chemistries within your ligand sets, it'll automatically cluster them. And what this does is it reduces the number of very dramatic alchemical changes that one would attempt in NES. So I can compare those 3 methods here. Again, these are separate runs for the CDK8 protein target. On the left is the correlation between experiment and NES predictions using OE low map. In the middle is the star map that has fewer edges, and on the right is the multi-star map, which is potentially more robust than the star map while having fewer edges than OE low map. And Pearson's R-squared, Kendall's tau, overlap coefficient, they're all fairly similar among these, but it's absolutely something that has to be assessed on a target and ligand chemistry dependent basis. So I told you that a nice thing about the star map is that they have fewer edges, but they are actually quite sensitive to the choice of the hub. That's the molecule that's placed at the center of the star. What we did here was we took the kinesin EG5 protein target. We selected 12 ligands to span a range of sizes and affinities. And then we just ran all possible RBFE calculations. And then from that, we can back out what the resulting predictions would have been if we had used any one of those ligands as the hub. So that gives us 12 different star maps and 12 different sets of predictions, each of which has its own Kendall's tau to experiment. And that's the distribution that's shown on the right here. These are the same calculations with the same method and the same ligands. But depending on which hub I pick, I can get a Kendall's tau between 0.3, basically useless, to 0.7, highly predictive. And it's this spread that really kind of motivated our deeper investigation into the dependence of accuracy on the selection of the hub. So now we took 10 different targets, each with 12 ligands, and we analyzed what those would look like with different types of hubs as the star map. So on the left, the strip chart that's labeled random, this is in fact all 120 possible star maps. And in each case, I'm taking the Kendall's tau for one star map and I'm subtracting from it the Kendall's tau of OE low map, which is our default. There is only one OE low map per set of ligands. So larger than 0 is where the star map was more accurate than our default OE low map. Lower than 0 is OE low map being more accurate than the star map. And so it's this spread that's concerning, and also the fact that the median here is less than 0, meaning typically if you were just to pick a star map at random, you may get a slightly less accurate result. In the middle shows something that's commonly done, which is to choose the co-crystallized ligand as the hub. And although that does move the median up a bit and it appears to shrink the variance, neither of these is statistically significant. There's simply fewer data points to represent the spread here. On the right, we have the approach that we're using. If you don't select a hub for the star map, we pick what is the kind of the common molecular core, the ligand that you've included in your set that is most similar to the common core between all of those ligands. This also tends to look a little bit better in terms of its distribution. Again, its range and average is not statistically different than the random set. So there is some real risk with these star maps, and that's something that you can assess with your target protein and your ligand chemistry. So to get on to some new features, we do, of course, provide you with a flow that will just automatically generate a map of whatever type you select. We are now introducing an interactive flow report. So after you've generated the map, you can go in and do things like add edges, delete edges. You can pick a hub and then ask that a star map be created from that hub. You can inspect that and then save it and use it to guide a future NES calculation. We also are now providing analysis of water, and especially structured water, in your protein ligand simulation. So this is a protein-bound ligand. The protein is occupying all the space that's mostly white because I'm not showing it, and you're seeing water molecules coming in and out of a semi-trapped water site on the left. And if we change that ligand, we're displacing some of those water molecules and fully trapping the remaining water molecule in there. So we now provide information about that in both 2D flow reports and in the Orion 3D viewer. The flow report will, in addition to what it's always done, which is show you the important interactions between the protein and the ligand, it will now show between structured waters and the ligand that are maintained over time. And then in the 3D viewer, you can pull up as spheres the locations and the occupancies of these structured water sites. And the idea then is that across your sets of ligands, you can look at those that either maintain or displace certain water molecules. You have either your experimental or your NES predicted affinities, and you can start to try and make relationships to understand which waters are critical to preserve and which you can gain value by displacing. So I told you that our affinity flows can help you make useful decisions during your DMTA cycles, and that indeed, as the methods become more computationally demanding, they do tend to become more accurate overall, although for a single target, it's certainly worth assessing a variety of methods. I showed you in the second part of the talk how you can boost your ligand capacity by, for example, 3 times by cutting your switches down from 80 to 20 and still get useful predictions in many cases. And then I talked about our interactive edge mapper, our structured water analysis. So really, this is our aim. It's to help you make better decisions about which molecules to make and which ones not to make in your weekly DMTA cycles. Thank you.
So Chris, thank you very much for that. I feel smarter already. So I've got a few questions that come in. I think things I'd like to explore a little more with you if you have a few more moments. You showed an interesting comparison early on between NES and Ensemble MMPBSA. Given that MMPBSA Ensemble uses an MD trajectory, what's the advantage that NES is bringing here that gives it the higher accuracy?
Right. So NES in the free energy estimate is directly including the context of explicit waters, whereas the Ensemble average MMPBSA is using those explicit waters to help guide the configurations, but it's a completely dehydrated system that is assessed. Well, it's an implicitly hydrated system that's assessed in MMPBSA.
More physics, better answers. Great. So you rightly focused a lot on how to improve efficiency in NES to reducing the number of switches or the calculation time. Have you looked at what happens if you increase the compute time or increase the number of switches? Does that have a positive effect on predictive accuracy?
We were unable to find a statistically significant effect there. So we've looked at doubling the number of switches. So 12 nanoseconds of STMD followed by 160 switches. And it's very similar. Now that's consistent with what I showed as that tail being very long.
Right.
We've also looked at increasing the switching time from 50 picoseconds to 200 picoseconds. And once again, we didn't see a broad, substantial increase. It is possible that for some targets, if you have a somewhat trapped water, that increasing that switching time could really help. So I think the answer there is, in the general case, we don't expect it to be very helpful, but there could be some targets where it's absolutely critical.
And those might include those that have trapped water.
That's right.
Okay. So you showed a lot of different ways of generating maps to relate one ligand in a set to another. Do you have some guidance for interested parties about how they might choose a particular mapping method for a particular problem type?
We default to OELO map, which is the method that I would absolutely recommend. It can be very valuable, again, on a target and ligand type of series context to assess whether a star map would be good, especially if you have a kind of a representative structure from a co-crystal. But if you were just going to pick one up and run with it, I think OELO map is for sure the way to go.
But if you have a closely related series for computation efficiency, you'd suggest a star map.
I would suggest that it's worth comparing them head to head. And then if the star map is looking robust, absolutely to move ahead with it.
Okay, thank you. So you rightly spent some time comparing sort of NES to other methods in the field, particularly FEP+, sort of something that a lot of people know a lot about. And you showed some quite substantial differences between them in a number of cases, and in others that they're really very similar. Given that they're approaching the same problem from different perspectives, do you have some speculations about why these methods might perform differently, substantially differently on the same target?
Well, the most substantial underlying difference is that FEP is a equilibrium method. So it attempts to sample as close to equilibrium as possible, whereas non-equilibrium switching attempts to sample very far from equilibrium and use a rigorous theory to estimate the affinity work, the equilibrium work. So for different targets, that could be a better or worse approximation requiring more switches. And, I'm not talking 80 versus 160. In a non-equilibrium approach, you could be looking at 80 versus 1,600 or something like that. We also have, vast differences in force field and differences in various settings within the methods. One place where we are seeking greater accuracy is for explicit formal charge changes between ligands within a set. And we're also looking to bespoke parameters for torsions.
So some of these are simply, if you like, differences in implementation, and others are more fundamental algorithmic differences.
Agreed.
Okay. So something that struck me as you were going through the focus on NES particularly is when you showed the relationship between the predicted and the experimental free energies, the slope of that line is substantially larger than 1. Do you have some ideas about what might be going on there? What's giving that rather striking effect?
So I'll say that collectively, that's a common phenomena for NES. TIC2, for example, was one I showed. It has a slope that's approximately 1. So it's not always the case. We have been investigating this for some time. It's not something that shows up in Schrödinger's published data with FEP+. It's not something that has been routinely reported for NEX for other people that have published those approaches. We have looked into a variety of sources. So, for example, we were recently checking whether the co-crystal ligand is one of the ligands with the highest affinity, which could lead to this type of bias. That turns out not to be the case across our sets, and really we're just still tracking it down. I will say Kendall's tau overlap coefficient rank order is the key as you're making decisions in a DMTA context. At the same time, we really should understand this, and we are continuing to work on it.
Okay. So to back out a little bit, you made a strong argument for the utility of methods like NES in compound triage, where you're trying to focus chemical, biological, experimental effort on the compounds most likely to be successful. If practitioners of NES wanted to choose even fewer molecules to sort of maximize their bang for the buck, how might they go about that?
Choosing fewer molecules to put into the NES calculation?
Yes, and then also at the end. So again, if you're thinking about holistic to maximize efficiency across the whole process.
Well, so what I demonstrated by a collection of kind of different approaches on the same sets of ligands was that you can get value at many stages down the funnel. And so instead of by applying ChemGauss4 to 30 ligands and then MMPBSA to 30 ligands and NES to 30 ligands, you can imagine triaging out your worst half ligands at each stage, for example. We don't have data on doing exactly that. Part of the reason is that we don't have that data is these are all strong binders in these data sets. And so if I kind of implemented that approach on this data, it's still not clear that that would be relevant in the context of, not all real ideas are good. Some of them are just very poor binders. And those are the ones that we hope ChemGauss4 will screen out.
Right. So thinking about this holistically, you showed some signal from docking. So perhaps docking could have a place in early triage to process more compounds to allow a higher fraction of good things to end up with NES.
Yes, but it appears target and or ligand series dependent. So I wouldn't just say you should always just triage as you go down the funnel. I think you need to develop some understanding of your system. I would carry everything through the first time I did it, and then I would go back and look and say, what would have happened if I had cut some of these ligands out at earlier stages?
So there are some subtleties to this.
ChemGauss4 is excellent for some of the targets I showed, and it is absolutely terrible for some of the targets I showed.
As we'd expect for any scoring function from docking.
Absolutely. These docking scoring functions are not made for this. It's amazing that it ever works, to be honest.
Yes, given how they're trained. So last thing, again, at a general level, from what I saw from the talk, you've talked exclusively about proteins that are cytosolic that exist in solution. Obviously, these days, there's a lot of interest in simulating proteins that are associated with or embedded in cellular membranes. Can NES be applied to membrane or membrane-associated proteins?
The method, theoretically, absolutely yes. If we're talking about water-exposed binding sites, like the orthosteric site on a GPCR, there's no particular challenge there beside the fact that we don't at the moment offer a tool to build a membrane around your protein and put it into the STMD to get the trajectory for NES. We are actively working on that. We do have some type of workaround where you can just restrain the part of your protein would exist within a lipid bilayer in order to keep it from unfolding during your simulations. However, we haven't even quantitatively assessed the accuracy of that approach yet.
So watch this space.
Yes, absolutely.
Okay, Chris, thank you very much. Thank you very much for attending. I hope you got out as much from this webinar as I did. That was fascinating stuff from Chris. And we look forward to seeing you at the next one in the series. So until then, goodbye.